It's a pleasure to be here. It's a pleasure to talk to you. And if you have questions, feel free to stop me. I will do a little bit of talk theoretically and a little bit of coding in MATLAB. Okay. All right. So the talk outline, first, we're going to do a GLMs reminder because the mixed effects models are an extension of the regular GLMs. So if we don't remember what GLMs are, it's good to remember now. So we'll go over them a little bit. But I'll try to go over them a little bit quickly because I'm assuming you know what they are. I'm assuming you know what GLMs are. And then we're going to be talking about what are mixed effects models and how to analyze mixed effects models. And then if we have time, I added 2 bonus slides, which we'll talk about them if we have time. Okay. So what are GLMs? Just as a reminder, let's say that we have a y, which is our dependent variable, משתנה תלוי, right? So let's say it's a reaction time, for example. And we have x, which is our independent variable, or we can have more than one x. We can have many independent variables, משתנים בלתי תלויים. So let's say age. Let's see how our reaction time depends on age, how reaction time changes based on age. So we can explicitly look at how y depends on x by fitting a regression model where we have our predicted y, it's a y with a little hat on it. It equals to b0 plus b1 times x. Okay, reaction time is some parameter b0 plus some parameter slope times age, okay? And we want the predicted y to be as similar as possible to the real y. That's a good model fit. Remember, we have loss functions that we want to minimize, or we use techniques. b0 is called the intercept, חיתוך. b1 is called the slope, שיפוע. No? Yeah. Slope. שיפוע or weight, משקל, right? Remember slopes and weights, same thing. Okay, so what do we do with this? Logically, let's say we collected the data and we fit the model and we got the 2 parameters. What do we do? Well, logically, if y is not linearly dependent, the reason it's linearly dependent because this is a linear equation, it's an equation for a line. If y is not linearly dependent on x, then b1 will get a weight of 0. Right? Because the changes in y are not predicted by the changes in x, right? Is that clear? So a unit change in x is not related to any change in y. Conversely, we can think about it the other way. If we see that b1 is significantly different than 0, the slope is significantly different than 0, then we can conclude that y is related to x. Okay? That's the whole game. So the whole game is to find these parameters and then see if they're different from 0. And then interpret them in the way that y is related to x by these parameters, or not related if they are close to 0. Clear? Okay, if the relationship is nonlinear in certain ways, we can use a GLM. So GLM is just an extension of a linear model for a line, where you have some, it's called an activation function or an inverse link function, that you take these parameters and you put them through a nonlinear function to map them to y, right? Oh, yeah, Adam, feel free. Okay. Is it clear? This is not new stuff, right? No? Clear. Okay. How do we interpret the coefficients? So we get these b0s and b1s or whatever. So first of all, the intercept, the b0, what does it mean to us? It's the average value of y, or the predicted value of y, when all of our x's equal 0, when all of the features are at 0. We can see it from the equation. b0 plus b1 times 0, this cancels out. b2 times 0, this cancels out, right? So whenever we look at the intercept, we say this is the predicted value of y when all the other x's are 0. And how do we look at a slope coefficient? How do we interpret it? Is how much y changes per 1 unit change in x1. This, in this case, is the b1 slope. When all other x's are 0.
You don't see your mouse.
Oh, okay. I'm sorry. Yeah. So wait, I'll do the laser pointer.
Does it work for you?
Oh yeah, I hope. Okay. So anyway, is that clear that the slope, they have a very natural interpretation for us in natural language. It's how much y would change per 1 unit change in x when all the other x's are at 0. And we can say in more natural language, it can be the effect of x on y controlling for, and I'm doing them in parentheses, all other x. Why is it not truly controlling for? Because to truly control for something, you have to really control for it in the experimental design. This is like a post collecting the data, we want to retroactively control for it. So we added it into the model as the other x's, and then the slope for our variable of interest is how we interpret it, okay? Great, so I'm just gonna run through this slide, which is, it's okay not to know it and not to remember it, but it's just giving a little bit of a flavor of the interpretation for all kinds of variable types. Yeah. But I think it's recording the wrong screen. That's okay, we'll be okay. So the first variable type is a continuous variable, right? So x1 is a continuous variable. So b1, we interpret it as the slope, and it is equivalent to a correlation between y and x1. It's not exactly a correlation. If you standardize it by multiplying by the standard deviation of x and dividing by standard deviation of y, it is the correlation value. Okay, but by putting a continuous variable x and a continuous variable y in the model, it's just like we did a correlation between x and y. It's the same thing, okay? So that's how we see how linear models can also do correlations. They're even more powerful than correlations, okay? If our x is binary means it takes 0 or 1. For example, it's 2 groups. For example, we have a healthy group and a group that has depression. So the slope, the b1, is not actually a slope. It is actually a difference in the averages of the groups, okay? And that's why we interpret b1 now as the difference in the groups, which is equivalent to a t-test, okay? Or other test between groups. It depends what statistics you use, okay? So you see, with one linear model, we can do correlation and we can do t-test, depending if we put in a continuous variable or a binary variable, okay? By the way, if we put both of them, we put continuous variable one, let's say age, and a binary variable, let's say group, then it's like what's called an ANCOVA. It's an analysis of variance with a covariate. So it can do both at the same time. Okay, now we run into our first problem. First problem, what do we, if we have a categorical variable that is more than 2 groups, that it can't be binary, it can't be 0 or 1, the model automatically divides it into many binary variables. It's called one-hot encoding. So for example, we have 3 groups, but the model translates it into 2 categorical variables, where the first coefficient will be the difference from our reference group to the first group, okay? And the second coefficient that we'll get will be the difference from the reference group to the third group. And if we want to see the difference between the third group and the second group, that the model doesn't give us that. We have to do subsequent post hoc testing for it, okay? So this is the first problem that you run into. Categorical variables become one-hot encoded into k-1 groups when you have k groups, okay? Because you have one reference group, which doesn't get an encoding, gets 0, and then the rest are encoded. Is that clear?
Let's assume that there are 3 groups here.
Here there are 3 groups, exactly, yeah.
As opposed to that variable x1 or x2 could be 2 values for the same individual.
Exactly. Here, so it's one-hot encoded means that only one at a time can be hot. Only one of them can be hot. Yeah, so this is exclusive binary groups. Like, are you Israeli? Yes or no. Are you American? Yes or no. Are you French? Yes or something like that. Okay, binary interactions are a little bit tricky. This is what happens when we have 2 groups, let's say healthy, depressed, and another binary variable, let's say, I'll go male, female. I think it's okay to go male, female. So now a person gets a value for both groups, right? So what the model and we want to find the effect between healthy and depressed, which is called the main effect, the effect between male and female, which is called the second main effect, and their interaction. So the model has to do this using 3 coefficients. The first coefficient is the difference between, let's say, healthy and depressed for the males, okay, for the 0 group in the other variable. The second coefficient is the difference between reference and, let's say, the females within the healthy population. And then the third coefficient is the difference in differences when you move from the reference group, which would be healthy and female here, to the group that's 1 and 1, which would turn here 1 and 1. So it would be male and depressed, okay? So with these 3 betas, we get all the effects we want, okay? However, we need to know what a reference group is, because these effects are from the reference group. They're also called simple effects. It's not a main effect, okay? Clear? Now it's going to get a little bit complicated. If you have a binary continuous interaction, so let's say you have...
So that's a good question about
yes.
The B2, you've drawn it between the orange group and the purple group.
Yes.
But also, is it also affected by the other 2 groups, by the orange and purple?
No, that's a great question. It is not. It's a simple difference between orange and red when x1 is 0. So it's because if we look at the equation, you see that B2 is, so when orange is 0, this cancels out, and this cancels out. So it's only B0 plus B2 x2. So it's only when, yeah?
So it's not, is it different from an ANOVA?
It's not, yes, it's not a main effect. It's a simple effect. It's like looking at post hoc inside an ANOVA within the healthy group, difference between male and female.
It's very partial.
Yes, it's partial. That's why you have to know your reference group. You can do post hoc testing, which will take into account the average here and the average there, or something like that. And then a binary continuous interaction is basically remember that when it's continuous, the coefficients mean slope. So now it does a slope for each group. However, so we should have a slope, let's say, for the healthy group and a slope for the depressed group. However, it doesn't just give us the 2 slopes, unfortunately. What it does, it gives us the slope for the reference group, let's say the healthy group, and then the difference between the healthy group and the depressed group at when x is 0 at a reference value. And then the interaction effect is the difference in slopes between the 2 groups, okay? So that way you can compare healthy and depressed at time 0, or you can see the slope for the healthy, or you do slope for the healthy plus the interaction effect, which is the difference in slope, and get the slope for the depressed. Okay, so it's a little bit tricky. And then the last thing is a continuous interaction, which is essentially, I'm just going to give the bottom line. The beta 1 is the x1 slope when x2 is 0. The beta 2 is the x2 slope when x1 is 0. And the beta 3, the interaction effect, is the slope change of slope, is how much the slope changes per slope. It's a little bit confusing. There's like people saying don't do continuous interactions because they're hard to interpret. Okay.
So for me, the biggest take-home message from this that I didn't understand from never learning that is I always kind of looked at it as in comparison to ANOVAs.
Yes.
And they're very different because it only works. The equation is when you take the other parameter as 0 and not averaging over it.
Exactly.
That's
So
for me the biggest difference.
yeah, so that's called reference coding. Reference coding means there's a reference group, which is 0, and then it's everything else in relation to that 0. There is a trick that I'm not going to be talking about that you can sometimes make it like an ANOVA, which instead of putting the groups 0 and 1, you make them negative half and half. Negative half and half is good because it's a unit change. And then all the other parameters are interpreted when it's 0, so it's like on their average. Okay, but I'm going to go with reference coding, and everything else that you want to get from the ANOVA, like the main effects, you can do with subsequent post hoc effects, and we'll see how to do it. Okay. All right. Just a note about generalized linear models. It's the same thing, except we're not talking about slopes now. We're talking about a little bit different things. So, for example, the Poisson one predicts occurrences per X or rate of a thing per counts per time. And the logistic, it kind of predicts probability per X, right? Remember this, that it's an S curve. We know this. Yeah. If you haven't seen this yet, okay. I wrote other link functions exist because this is the logit link function, but there are other ones that you sometimes use. Okay. So far clear. Mixed GLMs are clear. Now we're gonna introduce mixed effects models with 4 different intros. It's okay not to understand them all, but I think they give like different flavors of the mixed effect models and what it does. What? Yeah? Okay, the first one is mixed effects models are a solution to the independence violation. I'll explain. Let's say I recorded 9 neurons from 3 mice. Okay? Now, when I put the data from the 9 neurons in my GLM, the GLM assumes that I randomly sampled 9 neurons from the population and that each sample is independent of itself, right? We remember that in science we do independent sampling of the our test subjects, otherwise we can create bias, right? However, if I sampled these 3 neurons from this one mouse and these 3 neurons from this one mouse, they're not really independent. They have something, right? Some correlation between them, something like that, right? Okay. We say that the data is clustered. Instead of being independent, it's clustered. It came from similar clusters, which we want to control for. We want to solve. Okay. By the way, same thing if we, instead of doing 3 neurons, we record the same mouse on 3 different time points, right? Same logic, right? Or we record the same subject on 400 trials, right? So I have 400 trials, but they came from the same subject. Okay, so what is a solution? And I'm going to say it in math, but it's not that complicated. We add a random subject coefficient to correct for each subject. So every cluster of 3 will get another little coefficient or value in the model. It goes right here. It's a z value, they call it, to correct for that one subject, okay? So for these 3 neurons, they will get the same coefficients that the model will fit for all the parameters of the neurons and all the independent variables, plus a small or large correction factor for this mouse. And this mouse will get a second correction factor, and this mouse will get a third correction factor. And importantly, the correction factors are drawn from a normal distribution with mean 0. Okay, so it's not that we correct completely for each mouse, but we kind of correct and we make sure these correction factors, these extra coefficients that we add, kind of fit a random distribution with mean 0. Okay. This is an example from a paper that if you don't correct for clustering, you can get a wrong conclusion. I really like this example. They looked, it doesn't matter what they measured, but they look at all the mice and they see that there's a decrease between time 0 to between time 24 hours to time 48 hours. You see there's a decrease between orange and green. But if you looked at the individual mice, there's no decrease here, there's no decrease here, there's no decrease here. There is a decrease here. But mouse 2, they write it here somewhere. Mouse 2 contributed 43% of the cells that we measured. So it kind of dominated our sample. So when we didn't correct for the different mice, we actually got a decrease that looked like it's in all of the population, but actually it just comes from one specific mouse. Was that example clear? Okay, so that's why we got to do this correction. Okay, so we understand why mixed models, we're adding a small correction per cluster. Awesome. Second way to think about it is as partial pooling. Okay, so this is the second intro. Complete pooling means that we take all the data that we measured for all the neurons from all the mice or all the trials from all the subjects, and we put one linear model or GLM for all of the data without taking into account the different clusters at all. Okay, so you see here I got data from 4 different subjects. Some subjects have a lot of data, some subjects have few data, and I just fit a line in between all of them, and I get a B1, a slope of 1, let's say, okay? And we just showed in the previous example why this can be bad because it is dominated by one subject and so on, right? No pooling is the opposite. We fit one model for each subject, okay? So each subject gets their own slope, okay? So you see we have the slopes here in different colors, and then we do an average of all the slopes. Same thing in the table. You get... Yes.
Generally.
But you are sampling same number of variables.
Yes, but it's.
So it's not the case that one mass is more dominant.
No,
It's not. It could be if you're not sampling the same amount of trials, but if you're sampling enough trials, it is. What is happening here is that you do 4 different models and then the average of the betas within them, but you're not taking into account the uncertainty within each beta. Okay? And but it also a lot of time depends on your research question. If you're actually interested in the individual differences between the subjects, then you should probably do this method because you want for each subject it's their own slope. It's not just as a correction factor.
So that's an interesting question.
Yeah.
How much you can compare the slopes that you get from a mix, I mean, you don't have to answer it now, but from a mixed effects model, when you get different parameters per participant, if you, is it legal to then compare them?
It is legal.
To compare
The random coefficients?
the effects between participants.
Yes, so it is legal, and it will come in the third slide. It's you should think of it as regularized coefficients. So it's not the actual value; it's a little bit regularized. So partial pooling, what it does is this: it does fit a slope. You can think of it as fitting a slope for all the data with correction factors for each subject, like we said the other time. But also what you can think about is that it fits a slope for each subject. These are the correction factors from the actual slope, but they are because they're drawn from a normal distribution, and because they take into account the cluster size, so they are not as extreme and they're not as dominated when you have a small number of trials. So I tried to show in the picture, for example, the green subject here is kind of an outlier subject, right? But also it doesn't have a lot of points. So the random slope that it will get will be a little bit less extreme than...
So that's one question of legality kind of thing.
Yes.
And if you use the green as an independent measure together with the other factors and you're comparing it to something else, it's not an organic or independent measure of the green, it's green. It's affected by the others.
Green as it is affected by the population, yes.
Right, so if you use that as a comparison, then does that not violate the independence assumption of comparisons that you make?
It might violate okay, yes. So it definitely might violate because the correction factor that we give for green is dependent upon where all the other factors are, so they fit a normal distribution. Okay, so yes, it might violate. The other way to think about it though is to say here we have a sampling error for green. How do I know it's a sampling error? Because it's too extreme.
It's the point of justification, right? So my question of is it legal offers to compare, because it could be that that's the real one. Our best estimate is always going to be the measure, right? We say it's
not necessarily, because we can use priors from knowing about other people to know if this one is extreme or not. We do that all the time in outlier detection. So maybe we think of the real measurement that's independent for this person as a biased
like people do that.
So not really. People analyze the random effects, but when they're actually interested in individual difference, they use no pooling. They do one for each participant. Okay.
How do you determine this probability of the partial pooling?
Yes.
You need some prior probability of the random noise, which is not centered around 0.
You get it from the data.
Which probability?
Like, how do you get this probability around the beta 1?
So the beta 1, the average that you will get will be something here. By the way, it will be the middle between complete pooling and average pooling, right? It'll be somewhere in the center. And then these are the deviations from it, and we make sure these deviations fit random and normal distribution with mean 0 around the fixed effect, around the mean of all the data.
That would mean 0, mean around the fixed.
Yes, so all the deviations have mean 0. All the deviations have mean 0. Okay, all these correction factors.
Bitcoin is not something that it is not legal to do, right?
It's not legal to do it, but people do it in this building all the time when they take from neurons from 5 different mice, and they take 300 neurons from whatever, and they say, oh, I have 300 neurons, without saying, oh, they came from separate mice, without correcting for the mice.
It's very sad.
But then they do the no coding, so it's okay. Usually they do a process for analysis.
No, it depends. It's very often that people will pull.
General average, around all the.
Okay, and then the third way to think about it is a regularization factor. So just if we focus when we compare no pooling to the random effects, so the extreme participants get pulled more to the mean, right? Because we want to fit a normal distribution, so we don't want them too extreme. And participants with less responses get pulled more because they do not affect the average as much, or pulling them does not affect the loss as much, okay? So it kind of corrects for these two things, the extreme outlier participants and the participants with low number of points, okay? And then it's similar to L2 regularization where extreme coefficients get punished. It's kind of similar that we squeeze everything towards the middle, okay? So that's why you can think of it as a regularized regression, but not punishing the coefficients. Instead, we punish the extreme clusters, okay? So this was the third intro. And then the fourth intro is kind of a thinking from ANOVA ways as variance partitioning, is we say there's a lot, if we look at the complete pooling, we say all the responses from all the different subjects altogether, they have some variation in them, right? They have variance. Some of the variance is due to variation in the stimuli because we presented, let's say, different heading directions, so they have different responses, right? This is the fixed effect we want to measure. How y depends on x, right? How much of the variance we can explain with the stimuli. Some of the variation is due to individual differences per grouping, right? So if we have a lot of trials from subject A, a lot of trials from subject B, some of the variance will be because the difference between A and B. But this is not kind of what we want to measure, okay? And this extends if you have multiple grouping levels. So you can have, for example, different mice, but also different mice from different litters, right? Or from different cages. Maybe that's a second clustering thing. Or you can have different kids in different schools, right? But you can have different schools in different countries. So it's multiple clustering. And the random effects, the mixed effects models handle this very clearly. They add for each grouping variable that you put into, they give these correction random coefficients, right? And they can also do it for nested, that was nested groups, and they can also do it for a grouping structure called a crossed one, where let's say I take 10 words, which are the same words, and I present them to 10 different people. So I can take into account the grouping factor that is the 10 different people, and I can take the grouping factor that the same word was presented. So the word itself is also like a group. And the model, in one model, it can do both. So it can handle very complex clusters that we have in the data, okay? And then the rest of the variation is due to random error or unexplained error or noise, right? Something like that. And then we have this formula that this is the intercept, and then the fixed effects, the effects that we want to measure, and then the random corrections, and then the error, what's left over. Is that clear?
Mm-hmm.
Awesome. I want to talk about fixed effects versus random effects. So the fixed effects are the coefficients that are multiplied by the independent variables, and the random effects are these corrections that we give per clustering. Okay, so fixed effects, they capture a parameter at the population level, right? It's across all the clustering together, taking into account the different clustering, but it's like across all of them. It's not per specific cluster. Should be constant across subjects or clusters. Like that's what we assume. We assume that this is something that's across all the clusters that we see, but each cluster has some noise to it. These are of direct scientific interest. This is what we want to ask about. This is one to significantly test if they're different than zero and so on, right? And generally, yeah, these are thumb rules, yeah, rules of thumb. Not expected to change, which is the same thing as constant, okay? Random effects are cluster-specific effects for each cluster. It could be the person, if there are many responses from the same person. They're mostly relevant for capturing the dependence in the observation. Remember that the observations are clustered. And typically, they're of no direct relevance for assessing scientific hypotheses. So typically, we don't use them to ask questions. If we want to ask about individual differences, then we probably use a no pooling method, probably. Okay, so we should think as the mixed effects as adding our corrections. Okay, excellent. We will get very soon. We will get to coding. This is a slide that it's a little bit of bonus, but I'm just going to show that there's also a mathematical way to capture how much dependence is in the clustering. Okay. So let's say we have a group with 357 neurons, which come from 7 different mice. What's my n? Right? I want to know, like, what's my n? So obviously it's not 7, right? Because I have 357 neurons, so it's more than 7. But it's not 357 because neurons that came from the same mice, they're not independent. So we shouldn't consider them as completely different rows, completely different trials or data, right? So the answer should be somewhere in between, but it depends on how clustered they are within each mouse. If they're completely correlated within each mouse, it's going to be close to 7. If they're completely independent, right, there is no clustering within, it should be closer to 357, okay? And then there's a calculation, it's called the intra-class correlation. This is one formula for it, but there are a lot of different formula for it, okay? And they always give a number between 0 and 1. 0 means not correlated at all. So it means we don't need to add a random effects, right? We can just do the complete pooling. And 1 means completely correlated. So, okay, so we don't have any second observation from the same cluster. Doesn't add any more information after the first observation. We just need more information. So let's say in our example, ICC is 0.61. It's a lot. No, 0 is 357. Yeah, if I have an inter-class correlation of 0, then I can use all the neurons. They each give me different information. So I can 1, the neurons, only the mice, okay? And then you can calculate a magnitude of clustering, which is calculated according to this formula. And it's basically the average cluster size. And here the average cluster size is 32 neurons. So 32 neurons on average equal to 1 independent observation because they're so highly correlated, okay? And then we can just do...
Wait, what's M, what's D?
M is the average cluster size.
It's 51.
51, yeah. So it's on average, we have 51 neurons per mice. And D effective is 1 plus 50 times this correlation coefficient.
Okay, what does D stand for?
Something effective, effective independence or something like that, effective.
The smaller it is, the more effective the neurons.
Yes. Yes, and then what the number we actually care about is the n effective, which is our effective sample size, which is n divided by the effective, and then it's 11. So because they're so highly correlated, it's as if we sampled 11 different independent observations. Okay, it's common practice to calculate n effective, but I don't see it reported in like papers. It's like good for us to know how correlated we are within each group, and so how important it is to add the random effects, or maybe it's not important at all. Maybe we're in a very low correlation and then we don't need this correction. Okay, so it's good for us.
How can you tell in this example, maybe they came from different cases, right? And this could also be a random variable. So how can you tell if you add another, or does the random variable captures it somehow?
No, it won't capture if they came from different cages, unless coming from different cages will be within it. What?
It could be a fixed variable.
Yeah, but a fixed variable, we said, are the variables which we care about for scientific interest. These are not
So
the
once you have
corrections we
more
want.
than one random effect, how do you
Oh, so
aggregate over different random effects?
in this formula, I'm not sure because this formula gives me the intra-class correlation for one grouping. But maybe we can look online after and see if there's a way to do intra-class correlation for nested classes. I'm sure there are. Yeah,
And if the, שנייה אחת בעברית,
it's okay.
אם אנחנו מסתכלים על הניסוי שלנו, ואותו, כאילו כמה עכברים שונים הגיבו ל-16 מעלות, אז אנחנו גם נראה כאילו שהם correlated.
Yeah, but the heading direction is not, the heading direction is your stimulus. I'm going back here. And the change in their responses due to the stimulus is what you care about.
Yes.
So it's not a random grouping. Of course, there's a correlation. No, of course there will be a correlation between the responses to heading direction 16 degrees right and heading direction 6 degrees left. This is good for us. This is what we want to measure. How we change from the population changes from 16 left to 16 right.
Yeah.
This is not something we need to take into account in our model. It's not a clustering that violates the independence assumption. Yes.
What's called signal correlation.
Okay.
Okay. All right. Is this clear? Okay. So now I'm going to go over the Wilkinson notation, which is difficult. We had the chat talk up with it on the WhatsApp. So I'll just explain. When you put in the variables in your coding, and this works for MATLAB, R, and Python, as far as I know. So this is a little bit how you put in. If you put in 1, so you do y goes through 1, it gives you the intercept term, okay? If you put in x to the power of k, so let's say x to the power of 3, it gives you a coefficient for x squared, and x to the power of 3. So it gives you x to all the powers up till the power that you put in, okay? If you put in x1 plus x2, it gives you a coefficient for x1 and a coefficient for x2. But if you give in x1 star or times x2, it gives you a coefficient for x1, a coefficient for x2, and a third coefficient for the interaction between them, x1, x2, okay? If you only want the interaction, which you probably, in most cases, will never only want the interaction, you have to do x1, Nekudotai, if I say in English, column. Okay, so it only gives the interaction. If you do minus x2, it removes x2. So for example, we can do x1 star x2 minus x2. Okay, and then we'll get x1, x2 will be removed, but the interaction effect will be saved. Okay, and these are all kinds of different examples of how you can add them. Okay. Yes, excellent. So I didn't say this. Even if you don't put the intercept in, even if you don't type 1 in, it puts it in by default automatically. How do we remove the bias? -1. Very simple. Yeah, right? Because minus removes the intercept. Okay, this is for the regular GLMs. When we have our grouping structures in our mixed effects models, we're adding some grouping structures that are denoted with these parentheses. And this line is read per grouping structure, whatever, okay? So yeah, here they remove the intercept and they added a fixed effect x1 and x2, but there are no random effects. Here we have an intercept plus an intercept per grouping structure 1, okay? Is that clear? Here we have a slope.
What's the tag at the top? X2, sorry, I missed that.
Which one? Where?
Oh, at the end of the expression. Oh, it's just a.
Oh, it's just to close it as a string variable in MATLAB. Okay. So y is denoted. Okay. This is trick question. Let's go to this one. What did I fit in this model? Wrong. Why? Because by default you get the intercept. So you get intercept and slope plus intercept and slope per grouping structure 1. Yeah. What if I want the intercept?
This is what I think.
Yeah,
But it's not just MATLAB, it's general.
it's general. No, it's Python. It's in Python as well.
That's one.
You should check your code because if we have more than one grouping structure, so we add them in separate parentheses. And if we okay, so this is easy. We just add more parentheses. But if we use the same grouping structure in two different parentheses, then it will give us independent random effects, which means it will force the correlation between the random effects to be 0. Okay. Okay.
Yeah.
So here I ask for a random intercept and random slope per group. Let's say my group is my participant. I have 50 observation per participants. I have 10 participants, so I'll get 10 intercepts and 10 slopes. What is the correlation between the 10 intercepts and slopes? We don't know. We'll have to see what the model gives us. It could be that they're very high correlation. For example, if we interpret the slope as being bias and the intercept as being bias and the slope as being sensitivity, the more biased someone is, the less sensitive they are. So they will have a negative correlation. It can happen. However, when we write it in this formula, we're getting an intercept per group and remove the intercept and get a slope per group, per participant in this case, because the participant is a grouping variable. But when we put them in separate parentheses, it forces the slopes and the intercepts to be at correlation 0. Okay? So it will find these correction terms such that they are at correlation 0.
So what's the intuition for that? Why are separate brackets is correlation 0?
Separate brackets means independent random effects that we're adding. So independent would be correlation 0. Like these random effects affect the y independently, so they should be at correlation 0. That's where the intuition is. This is mikre prati, special case of this case, where this case would be 0. Why is it? It's not the default. This is the default. This is easier to write. This is if you want to spell out a specific case, like a special case. Okay. Excellent. And then we can have an intercept per this intercept plus an intercept per group, this grouping structure, and an intercept per a different grouping structure, right? It could be mice and then cages, or it could be, I don't know, other things. And then even an intercept per their interactions. So the interaction between the two grouping structures. Okay, so we can add them as much as we want. Important, default includes an intercept term, -1 to remove it. And binary or categorical variables are automatically transformed. So if I have in my data, let's say healthy, depression, I don't need to go and change it to 0 and 1 like we used to do 10 years ago in the old
1 month ago.
1
month ago.
Yeah, it's just the computer does it automatically for you. Or if it's categorical,
randomly what the 0 group.
Exactly, it doesn't decide randomly. It decides based on the alphabet. Whichever one is earliest in the alphabet will be the reference, and we will work in the example to change ourselves what we want the reference group to be. But we have to make sure we know what the reference group is and that it's a reference group that we want. Okay. Excellent. This is just the table from the original paper that introduced Wilkinson notation. So if you're more comfortable reading this math, so this is how it will be typed in MATLAB. Okay.
I have a question. Like you said, for the case of L, for her study, we need to assume there's a correlation between the random effects. I think that's true.
We need to assume, or you asked what you said.
Why you use a big graph parentheses, but not
Independent.
separate.
So I think it's the other way. I think is unless we assume they're independent, we will use one big parentheses, because the assumption of independence is like a stronger assumption, because it means we assume the correlation to be 0. And when we use the big bracket, the 1 bracket, then we say the correlation can be anything we want. We don't know what, we make no assumptions. The data will tell us, yes, the data will tell us what the correlation will be.
The first scene and the proof scene are, the correlation between them is zero or there is some correlation?
Yeah.
So we need to assume that there is some correlation. And then if we find out that no, so
Yeah, by the way, what you can do is you can first fit the model with no assumption of independence, and then you see what the correlation is. And if it's close to zero, say, okay, I'm going to fit the second model. You can do that. It's okay. Legal.
And the influence of brackets on the left, like the bottom line over there, that just works like
Algebra, yeah.
Like I could have done that x1 times x2
plus x1 times x. Yeah, algebra, yeah. Exactly. People don't use this. They write the full form. It's a trick that the programmers put in. Okay. Yes.
This notation.
Yeah.
That's what you call Wilkinson notation. So it was designed for GLMs, regular GLMs, and then it was expanded for.
That as far as I know, yes.
Okay. And then what's LMER? That's the same thing. That's Wilkinson.
Yes, but this is the paper that introduced the extension to the random effects. So this is like this is taken from the paper. So if you want to cite the paper, you look in the paper and you see this is why we wrote this formula or something like that. Okay. Yes.
אם השתמשתי רק בסוגריים, החלטתי שאני לא יודעת מה הקורלציה, ויצא לי 0. ואז אמרתי לה שאני רוצה להיות המיקסים, כאילו למה שאני אעשה שני?
It's similar, yeah. So you say if you get the correlation 0 between your effects within the group, so you move to the second one. Do I get the same corrections? Yes, more or less the same. It will just be more accurate, like it'll be because it can be like a little bit of a change, so it could be more calibrated or so. Because this will be close to 0. So you say, okay, let's assume it's 0, and then it can change the numbers a little bit and be more calibrated. In practice, I don't think it will change anything about the fixed effects.
If it is 0, this is not a wrong thing to do.
No, not a wrong thing to do at all.
The problem starts if
it's not 0 and you assumed it to be 0, you might get a not good correction term. Yeah, I think most people use unless if you have maybe computational powers to fit, it takes a long time, so you do it you force it to be 0, so it's easier for it to calculate or stuff like that. Okay. I want to do a quiz. This is a random intercepts, but the same slope for participants. How are we going to write it? Okay. Random intercepts. Random intercepts.
So it's 1 per subject.
And it's the same slope for all of them. So we have a slope. So it is 1 per subject, yes. Yes, but we have to have an x because there's a slope. That's the same slope for all of them. And these two ratings are equivalent, right? Because we didn't remove the 1. Here, the opposite. We have random slopes per subject, but the same exact bias, intercept. For example, we set it to be at 0 due to some assumptions that we have. Or
X minus 1.
Exactly, that's the trick. It's x and minus 1 plus x per subject, okay? And then here it's random intercepts and slopes, which are the most common, is 1 plus x plus 1 plus x per subject, or in short, for notation. Okay?
Why did we do minus 1?
Because here we said there's only 1 intercept for all of them.
You can check it out.
Yeah. Okay, so let's do a complicated example.
You can add it to your home.
Okay, I'm gonna go through this. We want to predict firing rates from different neurons. We have 2 neurons type A or B. Some of the neurons come from the same mice, but we have 2 different mouse types, wild type or mutant. And we want to see if there's a difference between A and B. And we also want to see if there's an interaction with mouse type. And we also have to correct that some of the neurons came from the same mouse. So how are we going to write it? So I'll just show the answer if you're thinking. It's not that difficult. We go, the firing rate is by 1, I just include an interceptor, plus neuron type, which is the A-B neuron type, plus mouse type, which is wild type or mutant, plus neuron type, interaction, mouse type. And we correct for an intercept and the neuron type per mouse. Here I decided to correct for both, okay?
But it's like usually if you, for the neuron types, if you only have 2 items,
Yeah.
I mean, it seems they don't usually use it as a fixed effect.
No, if you have two items as a fixed effect, it's like a t-test. It's like the comparison between the difference. It's like a binary variable. Okay, but we remember that we don't have to write A and then B and then their interaction, because there was a shorthand that if you just put the star between them, you get this one and their interaction. Okay, and also we don't have to explicitly write the intercepts because it automatically includes them. Okay.
Now, what about the fact that random effects rely on a Gaussian distribution?
Yes.
And don't we need more than 2?
No, but this is in the grouping variable. Let's say we have 70 mice here. Okay. For each mouse, we do a difference between the 2 neuron types. Okay.
So that per you need a decent amount of.
Yes, and that's a good question of how many different clusters do you need to correct for that will be a good correction. I saw somewhere, I think 5. But I don't know if that's like a real thing, or because I saw it in a blog, so I don't know if it's a real thing or not. Yeah. Okay, so let's do, we can do this example or we can skip this. Okay, I'll do this example just to show you how we interpret the results, okay? And then we'll do coding. So we have, doesn't really matter, but we showed 10 positive words and 10 negative words of different length and frequency to 30 healthy subjects and 30 depressed subjects with depression. And we measured their reading time. So we have this table. I am only showing 4 words per subject, but let's say we have 10 positive and 10 negative words. Okay, so we have to put in one big table. For each word, we have its reading time. That's what we're trying to predict. We have its frequency, its length. Is it positive or negative? What was the word itself? We're not going to actually include this in the model. We will include it as a grouping structure because all the words smile kind of form a group. And is the subject, is he depressed or not, healthy or depressed, okay? And so the formula that I'm putting is I'm first saying, I'm putting in the word length and word frequency as variables, not of direct scientific interest, but I want to make sure all the effects that I found on the other variables are when I take these variables into account. So these are the variables I take into account, so I have to put them in the model. And then word emotion interaction is depressed is my research question, which is there a difference in reading happy and sad words? Is it different for people with depression? Okay, so I need to find an interaction effect. And the grouping structures, so I'm adding intercept and how the emotion word changes per subject. And I'm also adding the reading time per word. Because the word smile, for example, again, appears 20 times in the data, or 30 times in the data, or 60 times in the data. So I'll need to correct for that cluster, okay? Is this clear? This is a classic formula for a scientific paper that researches this. And then, yeah, these are control variables. Emotion, again, is the reference group is that it's positive, and is depressed, the reference group is that it's healthy. Okay, and now this is what we get out. This is what the model tells us. So we get fixed effects. So the first fixed effects is the intercept, 200, which we interpret as reading time for when everything else is 0. So for a word of length 0, with frequency 0, with emotion positive, for the healthy participant, okay? Not very meaningful to us. For every word length, we add 5 milliseconds reading time. So every unit increase in word length, we add, again, not very interesting, but we should have this. Same thing for frequency. For every word that is more frequent, it's negative 20 milliseconds reading time. Not very interesting, but we should have this. Yes, Austin?
Would you want to add a variable intercept as well per subject? If subjects have a
For the-
variability in reading time?
Yeah, so-
Subject A is a really.
Yes, so if subjects have a variability in how the word length affects their reading time, yes, you would add another word length random
The
effect.
interaction.
No, just the word length per subject, because we say word length affects subjects differently. But if we assume that the word length affects subjects the same, which is what I assumed here, I didn't add it. What you would actually do is do one model with, one model without, and then compare the models. This is where it gets interesting. So emotion we get 10 milliseconds extra reading time to move from positive to negative. But we only get it for the healthy population because we're in reference group. So healthy population takes 10 milliseconds more to read negative words compared to positive words. Okay, that's how we interpret this. Is depressed gets 50 milliseconds more. So this means 50 milliseconds more for the depressed population compared to the healthy population, but only for positive words, right? Because it's when everything else is zero. And then this is the interaction effect. Emotion is depressed is negative 30, which is our effect of interest. And it's when you move from positive healthy to negative depressed. So you move plus 10 because you moved from positive to negative, plus 50 because you moved from healthy to depressed, minus 30. That's why I showed it. Yeah. Okay, is that clear how we interpret them? And then we do a statistical test on each one to see if it's significantly different than zero, and so on. Okay. We also get random effects, but we don't get the actual full list of random effects. Instead, we get, for every random effects, we get its standard deviation, which shows kind of how much variance it is, how much variance it accounts for. And these,
because the mean is zero. That's because the mean is zero.
The mean is zero, yes. No, but I'm saying we don't get a list of the whole 50 random effects for each subject, for example.
Oh, okay.
We just get the standard deviation. We can extract the list of the 50 if we want. But what do we look for here? We want to see that it accounted for a good amount of variance. So let's say we see that the subject intercept is, let's say it's considered pretty big, because there is a big difference in the baseline reading times of subject. But the subject emotion standard deviation is pretty small because the emotion affects us pretty much the same or something, okay? And for every 2 random effects within a grouping, we also get their correlation. Okay, and here there was a very small correlation, so maybe I could have moved it to different grouping, okay?
Say it again.
So this is the correlation between the intercept and the word emotion per subject. Remember, that's what we had the whole discussion about, okay?
And that's because it's within one bracket.
It's within one bracket.
Theoretically, here you could separate the intercept per subject and the word emotion per subject.
And then this would be 0. You won't have it in the model. It's one less.
It's exactly the example that we talked about.
Yes. And then here's what I want to make sure. The model also prints something which is observations. There will be all the observations that we have. So we got to make sure it's the observations. Fixed betas will be 6 because it's the. Because the intercept and all the betas that we added according to the rules, random betas will be 140. Why? Because we have 60 subject intercepts and 60 subject slopes and 20 word intercepts, because that's what we added, okay? And then the covariance params are 4. These are the covariance parameters. Why? Because there are because standard deviation is the standardized variance and the correlation is the standardized covariance. So this is the standardized covariance items, okay?
Why do you have the beta 0 plus intercept? Isn't the beta 0?
No, this is the interaction. Yeah, sorry. That's how we should think of a different way to do interaction because it's the same 3 letters as intercept. Okay, are we ready to go?
This was the place that we found
Yeah, because we saw that we didn't have enough covariance parameters. So I noticed that there were a lot of correlations that were missing from the covariance parameters, and then we noticed that we forced them to be 0.
So how would you summarize the random effects here? You do have random effects per the intercept and word intercept?
Yeah, you can also do a significance testing, by the way, to see if they're significantly different than 0, but I wouldn't do that. Instead, I would fit 2 models, one with them and one without them, and see if the models are different. But I wouldn't summarize. It's more for myself. I'm not going to write about this in the paper. I'm just going to do for myself like a sanity check to make sure I'm doing well, okay?
And then the fixed effects, it gives you numbers, and how do you assess those statistics?
Great question. I have a slide on it soon, but I'm just going to do a MATLAB example and then we'll do it, okay? But you have to do significance testing for each number. All right, so I preloaded, and what I'm going to do in MATLAB, I'm going to do a binomial regression, a logistic regression. So I invented other data. We have subjects. Some of them have depression, some of them don't, okay? We also have a depression level, which is no, minor, and severe. And then they were reading words, but sometimes they would skip a word. So I want to model the probability of skipping a word in reading. Okay, so it's clear why it's a logistic regression, right? Because probability of skipping. And I want to see if it depends on the word length, if it depends on depression, and if it depends on the pupil dilation at the exact moment or something, okay? It's a kind of a clear example. So first I loaded the data. First thing I do is that I make sure that the is depressed variable is categorical. And I want to see what the categories that it did for me, okay? So I see that the categories are no and yes. So no is the reference group and yes is the depressed. Yeah, because that's how it's the first, okay? And then I do my formula. This is the formula that I did. So it's, I only add an intercept per subject, no more, okay? And then I fit the model using fit GLME, which I give it the data, the formula, and I tell it logistic, which is distribution binomial, okay? And now we will get, still busy. Okay, and now we get all the things, all the goodies. So the first thing, remember what we showed, number of observations, how many fixed effects coefficients, how many random effects coefficients, pop quiz. Why are there 7 random effects coefficients? No. Because we had 7 subjects in the data. Okay, because I have an intercept per subject and we have 7 subjects. No, I didn't show that we had 7, but this is what you should think about, okay? And then this writes out the formula in full, no matter what shortcuts I did. So this, we look at it to make sure it's what we wanted. These are model fit statistics, which I don't know how to interpret by themselves. Usually we interpret by comparing 2 different models, but it gives you the AIC, BIC, log likelihood, right? Good stuff. And then these are the fixed effects estimations. So this is the fixed effects for the intercept. This is for the is depressed, yes. It means moving from healthy to depressed, right? From the reference group to the yes group. Okay. We see it increases the probability of skipping a word. I see it because the coefficient is positive. Word length decreases the probability of skipping. The longer the word. Yeah, but this is a true finding. Longer words are harder to skip. Pupil dilation kind of increases, but less. It also gives you the standard error for each model, for each coefficient, and the t-statistics and the p-value of a t-test that it does to see if it's significantly different than 0. And what jumps here immediately is that word length is significantly different than 0, is depressed, is not, and so on. And it gives you lower and upper confidence interval values, okay? And then we look down and we see these are the standard deviation estimate for the intercepts, which are pretty big. So I think I'm glad that I included it. Okay. Done with this example. I think so. And then you can plot partial dependence. You can do plots with this model. But for some reason it was bugged in my MATLAB. Like it worked earlier and it doesn't find the function and I can't debug it. I didn't debug it in time, okay? But it gives you all kinds of plots of the model estimates, okay? It's good stuff. All right, I'm going back to answer a few last questions. So sanity checks that we have that are very important. Make sure you know what the reference categories are. You can use categories or reorder cats or set cats to reorder them. Okay, important. Verify that the model converged without any errors. Because this model, we know that's not an analytical solution. They use all kinds of optimization techniques like gradient descents and other stuff. So sometimes the model doesn't converge well, and then you get like a printed text warning, the model did not converge. And then you have to see why, and you have to look online for the specific bugs that you have. It could be that you misspecified the formula. It could be that the data is not handled well, or it could be that you're adding too many parameters and it just can't optimize for all the parameters. Okay, classic stuff. Verify the model specifications, what you needed, interpret the formulas, count the parameters, assess the model fit. You can plot the residuals or plot partial dependence plots and conditional independence plots. I forgot what they're called. And see if the parameter values or direction makes sense. So we saw how we looked. Oh, this is positive. It increases the probability. This is negative. So you should look at your own models and see if they do that. It's important, I think. Okay. Awesome. Model comparisons and selection. Same rules of model selection for GLMs apply. We have two models. We want to select between them. We use one function which is called compare model A and model B. Okay. And then any random effect with a negligible standard deviation can be discounted. And we can see it with the compare function. We'll do a model with it, a model without it. We'll compare between them and we'll see there will not be a significant difference between them. Okay.
Basically, you're just adding parameters to your model.
Exactly.
This is like.
Exactly. So I want to do
So what is the comparison?
So let's see if you get it from the example. I'm going to do two formula. Can you see? One with pupil dilation and one without pupil dilation. Okay. I'm going to fit both of them. And then. No, it's for the same data structure. Okay, so I have the two models and then I'm using compare and it does a log likelihood test between the models. I hope you can see the bottom of the screen. It gives me the AIC, the BIC, the log likelihood, and the p-value for the difference in fit between the two models because it's a log likelihood test. So it's a difference in fit. If the difference in fit is not significant, then we can allow ourselves to take the model with the fewer parameters. Because we say we take less parameters and we didn't significantly lose fit. Is that clear? Same, and you can do it with the actual parameters like pupil dilation, or you can do it with the random effect parameters. I think, Adam, I don't know if you teach model comparison, but I think it's like very simple to know, and we should be able to try different formulas.
We just normally look at the difference in AIC and BIC.
Oh, okay. We can look at the difference in AIC here and see it's a small difference. That favors yeah. Okay. I think we should be very comfortable in trying different formula, trying what works and see what we can draw. However, there are rules to do this that I will talk about soon. How much time do I have? I have 15, 20 more minutes, right? Did I kill you guys? No, not yet. Significance testing for the beta coefficients is a controversial topic. It's complicated and controversial. So the way that we showed, we did the t-tests on the coefficient, but some people believe that there are violations of assumptions for the t-test when you use the mixed effects models, so you shouldn't do those. So there's a blog that I will link to at the end that gives all the rules to do it, or the suggestions, but these are my suggestions. If the betas actually correspond to your research question, so you actually want to test if the beta is significantly different than 0. The first one is, it's called a wall test, but it is the t-test if the coefficient is significantly different than 0. Okay, and then there are different methods to calculate the degrees of freedom, which is only relevant for small samples. When you have large enough samples, it doesn't matter what degrees of freedom you have, it's an approximation. You remember the t-distribution approximates the z. Okay, so this is what we did. This is the first recommendation. People do that. Better is to do a likelihood ratio test for the model with the fixed effect and the model without the fixed effect. And we see if the model fit is significantly different, we say, okay, we need this fixed effect. Okay. But it's not always possible because sometimes you want only an interaction effect or something that, so you can do, or actually if you only want the interaction, you can do with or without, but sometimes there are interaction effects that you need to take care of. And then a third method is more complicated, is a parametric bootstrap test, which is it's kind of a simulation test. You've heard of bootstrap tests? Yuval Ohev? Okay, so this is the most recommended one. However, in all the papers that I read, people did the wall test and they got published. So, okay.
It's enough.
Yeah.
They got no results with this job.
What happens if I want to compare? Let's say I have a categorical variable with 3 groups. I have the reference group, but I want to compare between group 2 and group 3. Right? Remember the example? So the betas will not correspond to the difference because I'll get a difference between group 2 and group 1, difference between group 3 and group 1. But I want 3 and 2. So I use the function coef test, and that's what we're going to do. But coef test, you have to tell it what you're comparing to what. Okay? So first of all, I'm doing instead.
Just redefine the parameters. That was what interested you. You could just make group one.
Oh, yes, but let's say you have 3 groups and you want to test all the difference between them. Instead of fitting the model 3 times or 2 times, right? So there's a coef test on the same model. It's simpler. It's like a post hoc test in a way. So I have, instead of depression, I'm going to use 3 depression levels. So it's no, minor depression, severe depression, but we're going to treat them as 3 different groups, okay? So I'm going to refit the model. So first, I'm going to make sure it's categorical. Remember, we want to make sure it's categorical, and I want to know what the reference group is. And oh no, the reference group is minor, and then no, and then severe. I don't like this. So I'm reordering the categories to be no, minor, severe. Okay, and then I'm going to print the categories again. Excellent. So now the categories are in the order that I like. I know what my reference group is. Okay. Now I'm going to just fit the model. Okay, it's a new model. What am I doing here? Which group will be the reference group? Okay, so I reorder the data, and then we see this is the coefficient corresponding minor different than no, and this is severe different than no, right? And we see that if we look at the p-values, minor is not significantly different than no, but severe is significantly different than no. But we want to check if severe is significantly different than minor, right? Classic case. So we use coef test. We put in the model and we put a vector, the length of the betas, telling it which betas to compare. This is the same notation for ANOVA comparison post hocs, if you know it. So here I'm saying it, give me a comparison between the second coefficient versus the third. Why is it second versus the third? Because one is positive, one is negative. Okay, so the second one is minor versus the third, which is severe. Okay, and then you can also, if you want to do a comparison between, yeah, you could, but let's say you want a comparison between intercept, or I don't know, second and third versus the fourth. So you do minus half, and 1.
Okay. They're not necessarily groups, like you've got their intercept and word length, for example, is the fourth.
Yeah.
Is a different parameter.
It's a different parameter, so you get 0. Right, in my example, yes. I'm saying, let's say you have 7 groups and you want to compare the first 3 versus the last 4. So you do -3, -3rd, and quarter. Okay? Yes. Of course, you want to know what you're comparing. You want to know what's inside this vector. You don't just type out things. And unfortunately, I don't know why, it only gives a p-value. It doesn't give anything else. And the p-value is not significantly different. I don't know. So I read in MATLAB, like how can it to do it, but I just saw it gives a p-value. Yeah, so that's what we get. Okay. All right, these are some good MATLAB functions that you can do after you fit the model. So the coef CI gives you the confidence intervals for the coefficients. It's the coef test. It's the compare between the models. If you want, I don't know, plot the residuals, or you want just the random effects from the model, or you want just the residuals, good stuff, okay? Do you have any questions? Because I'm done with my mixed effects models, and I have 2 bonus slides that we can go over. Yeah, do we have energy? We don't have to. I have energy. Yeah. Okay, what?
If you have energy, so
Okay, good. So the first bonus is a slide of how do we choose which predictor variables to include. Okay, so this is something Yuval told me. What is the bad way to choose which predictor variables to include? Just throw everything in and see what's significant. That's not a good way to choose which independent variables to include. What is the good way is we use something that's called causal inference theory. That sounds complicated, but it's very simple. It has 3 rules. So we're going to go over the rules, okay? The first rule, the thing we need to remember is that when we include a new variable in the model, it's as if we're conditioning on that variable, right? It's as if we're taking care of that variable, and all the other variables will get their effects after conditioning on that variable, okay? בהינתן המשתנה שהכנסתי, כל שאר האפקטים יהיו בהינתן המשתנה הזה. So it's a way to clean out unwanted variables or to split between two different variables. For example, in Shir's paper, she split between the previous choice and previous stim by including both of them. And then what you get for previous choice is conditioning on the previous and so on. Okay, so let's go over the 3 rules. We'll remember the 3 rules, okay?
So the thing is that if there's some correlation between them, then who does that correlation get attributed to? The question. If you condition on the one.
Yes. So it's like partial correlations. So that each one will get the partial correlation.
Where does the joint correlation?
I think it's split evenly between them.
They're not really a partial. It's like, so given basically says you find a correlation between, let's say you got I don't know what, firing rate is dependent on the variable x and y.
Yes.
So if you calculate the correlation, the firing rate in x given y, that will just give you the part of y that is correlated.
Yes. So it's not full conditioning. I agree. It's like above and beyond but because it fits together, then it's not full conditioning. I agree. I need to see if it really does fit them both. It attributes it evenly. It could be attributing based on the order that you put in, and then it would be a partial correlation, but the reverse way around. But I don't think it is, because I think it's order independent. I'll think about it. Yeah. All right. So the first rule is that including a confounder variable c takes care of confounding x and y. So the example that people give is that there's a correlation between how much ice cream you eat per day, or how much ice cream is eaten in the country per day, and how many drownings were in the country that day. Why is there a correlation between? Because in the summer you eat more, but also people go to the pool more and unfortunately drown more, right? So if you just predict drowning from ice cream, you will get a positive significant correlation, right? A significant beta. But if you include the temperature in your model, you will see a significant correlation between temperature and drowning, but no significant correlation between ice cream and drowning. It will take care of the confound, okay? So always include confounder variables. Easy rule. Anything that can confound the model that you measured, include them, okay? Second rule, including a mediating variable m cancels the indirect effect of x on y. So I'll give the example. Let's say x is a diet. Are we going on a diet or not? And y is our weight at the end. But we're also including how many calories we ate per day. Okay? So had we not included m, we would see an effect between people who go on a diet and people who don't go based on their weight. For example, let's say the diet works. When we include m, we will see a correlation between how many calories you ate per day and your weight, but we won't see a connection to the diet, because all the information, all the effect of the diet is through m. M takes away this indirect effect, okay? Is that clear? So m is called a mediating variable. And the rule is, do not include the mediating variables unless it is your research question. If my research question is, did the diet work or not? I included the mediating variable and I say, oh, the diet didn't work. There is no positive coefficient for diet or no diet. Of course not. All the correlation will be on the calories coefficient. But if my research question is, how does the diet work? Does it work through calories eaten or through something else? Then I do want to include it. And then I will look here, okay? So always include confounder variables. Sometimes include mediating variables based on your research question. Okay, clear? Including collider variables creates a false effect of x and y. So the example we give is that, let's say I like a burger place if it has a tasty burger or if it has tasty fries. These both cause me to like the place. And then I want to see, is there a correlation between having good burgers and good fries? Right? So if I only look at the burger places that I like, I will see a negative correlation between them, because I like them if they either had good fries or they either had good burgers. So in my in the observed data, I will see a correlation. This is the same way of saying that if we include a collider variable, which is a variable that is both caused by the dependent variable and the independent variable, then it will create a false correlation in our data. This is called collider bias. So we never include collider variables, okay? this is also similar to selection bias. If we only pick people for our survey, people who like to answer surveys, then we will see a correlation about how much they like to answer surveys or something like that, right? Okay, it's the least clear of the rules.
Yeah, this is using it as a selection bias, but
Yeah.
it's not a selection per se.
But when you condition on it, you create the false selection, because conditioning on it would create the false association. Yeah.
So O is being a discrete variable in this case.
O being a discrete variable I like or I don't like. Yeah, for example. Okay. So is that clearer? Was that good? Okay, I'm gonna take 10 more minutes. We're gonna be talking about my second bonus, which is the this works. The properties of the logistic regression. And I think this is a cute thing. I don't think you have to know this, or Adam, you can correct me if you want your students to have to know this. But it's about, remember that we said that in a regular linear model, we interpret the slopes. How do we interpret them? As the change in y per unit x. Because that's what a slope means, שיפוע. כמה y משתנה לשינוי ב-x1. יחידה אחת, 1 unit of x. How much does it change y, right? We know in the logistic regression, it doesn't work that way. So how do we interpret logistic regression coefficients? Does anyone know? Anyone? Okay, we interpret them as log odds ratios, and I'll explain. The logistic, the y of the logistic regression, what's going inside here before the link function is in the log odds scale, okay, not on the probability scale. I'll type it up, and then we can converting between the log odds and probabilities is complicated and unintuitive. So now we will go through a lot of math in the last 10 questions. Maybe I shouldn't have done in the last 10 minutes. Maybe I shouldn't have done in the last 10 minutes. But if you keep your concentration with me, you will learn like simple tips to make it a little bit less complicated to move from the coefficients that we get in logistic regressions into probabilities, okay? Okay, so let's start. Odds. Odds are defined as P divided by 1 minus P, where P is the probability of something. In regular language, we say 1 to X odds. So let's say I have a chance of 10% of winning something, the game. So I have 1 to 10 odds. No, I have 1 to 9 odds. Okay, because I have 10% of winning and 90% of losing. So it's 1 to 9. So I say 1 to 9 odds. In Hebrew, I think you say סיכוי יחסי. יש לי סיכוי יחסי של 1 ל-9. 10% winning, 90% not winning, okay? These are odds. When the odds equal 1, what is the P? חצי, half, because I have half of winning, half of losing, so it's 1 to 1, so it's 1. That's a good way to say it. For every 9 losses, I will win once. That's what the odds mean. Yes, that's a good way to say this. Yes, I like it. Log odds is we take log of the odds, right? We use the natural logarithm. So if the log odds is 0, this odds of 1, so the P is 0.5, half. If we get positive log odds, means P of winning is bigger than half. Negative log odds, P is smaller than half. That's why when we interpret the coefficients, remember we saw one of the numbers was negative, and I said it decreased the probability of skipping, and positive numbers increase the probability. Okay? Awesome. Odds ratio is a new thing. It's not odds. It's odds. Odds ratio for group B compared to group A is the odds of B divided by odds of A. So let's say there's 2 groups, one that didn't get medicine, one that did get medicine, right? So they both have an odds of dying, unfortunately, but we want to see how much the medicine works. So we look at the odds ratio. So we see what's the odds of dying in group B compared, divided by the odds of dying in group A. And hopefully it's a low number. Hopefully it decreases the odds of dying, okay? So this is like סיכוי יחסי, יחסי, or יחס סיכויים יחסיים. I don't know how you'd say it in Hebrew. It's the ratio between odds, okay? Is that clear so far? Awesome. If the odds ratio is 1, it means there's no change in odds. If it's less than 1, B reduces the odds compared to A. If it's bigger than 1, B increases the odds compared to A. Okay? Beta coefficients add up on the log odds scale. So log odds scale. So let's do an example that y is b0, some intercept, plus b1 times the binary variable is depressed, healthy or depressed, okay? So b0 will be the average y for the healthy population, which is the reference, and b1 will be the difference between healthy and depressed, okay? So we'll do a little bit of math. Let's say we got that b0 is 0.2 and the b of depressed is negative 0.8, okay? So converting them into probabilities in the normal old way, we do, what's the probability that the reference, that they get 1? So it's the inverse log it of 0.2. Remember, because this is just the reference group. And we see it's 0.54. So they're a little bit biased. Let's say this is, let's calculate, this is their probability to say right or something, okay? To click right. So they're a little bit biased to the right, but they're more or less even, right? And then we look, what is the probability that the depressed group, y will be 1, they will hit right? So we go the log it for the depressed group, which is the reference group, plus the difference to the depressed group, so it's minus 0.8. So it's a log it of minus 0.6, which is 0.35, probability of about a third, okay? So we see that a negative beta is a decrease in probability. In this case, it's a decrease in about 20% probability, or maybe you can say it's 3/5, right? But it wasn't clear to us from the numbers that this was the decrease. And also it kind of depends on both numbers. That's why probabilities are a little bit complicated. Okay, a depression leads to a reduction in P compared to reference. But how much reduction depends on all the coefficients, because we have to put them all in the model, and it gets complicated, okay? So now this is the trick. The trick is this. If we look at the odds for the reference group, we only do e to the power of the log odds, right? Because e to the power of log odds will be the odds. And we get that it's odds of 1.22 to 1. So it's a little bit more likely than not, because it's a little bit more than half. Remember this? If we look at the odds of the depressed, we can look at the log odds again of the depressed. So we put in all the coefficients, 0.2 minus 0.8, e 0.6, 0.55, which means that y1 is half as likely than y0, which is equivalent to our 1/3 finding, more or less, right? For every time they do 1, they're twice as much to do no, okay, so they're half. But again, this is complicated. We have to put in all the coefficients. If we want to do the odds ratio, we go the odds for depressed, 0.55, divide by the odds for reference, 1.22, and this is the odds ratio. So this is, remember, odds ratio of 0.44, odds ratio is less than 1, B reduces odds compared to A. And now here is the shortcut. If we had just taken e to the power of the depressed coefficient, we only look at this, we don't look at anything else, we get the odds ratio immediately. Okay, so we can look at every coefficient that we see, we do e to the power of that, and we get the odds ratio. So every coefficient is the log odds ratio. Okay, so that's kind of a shortcut to see by how much it changes the odds. Okay, to convert into probabilities, it's confusing because odds are not probabilities, they're a probability divided by the complementary probability. But if we train our brain to think in odds, which I've been trying to do and it's difficult, maybe it's more interpretable. Okay? All right.
In the medical literature, they use that a lot.
Medical, yeah, because you want to compare the group that got the placebo and the group that got the...
Also, though, it's like the standard language there is the chances of, given these insane, the chances of having, a child with Down syndrome is 1 in 10,000.
Right.
But if you're of a certain age, the odds are 2 to 1. Basically, it's exactly the language that you used.
But if we use a lot of binomial regressions and logistic regressions, we can think in odds ratios. It's natural. It comes naturally with the logistic regression. Okay. So depression leads to an odds ratio of 0.449 compared to reference. So we got immediately by doing e to the power of the coefficient of regression of depression. Okay. Cool. Okay, so this is a picture to show that generalized mixed effects models are like a Swiss Army knife, that they can do correlations, ANOVA, ANCOVAs, GLM, regularization, repeated measures, t-test. They can do all that kind of stuff within them if we need them. Any questions? Yes. Stamp. No, it's just one more tool that we need. I will say it's okay also not to use them. I think, in my personal opinion, it's okay also not to use them. If we know our data, we should be able to see if we're making mistakes and like that error of that one mouse that dominated. We should be able to know that by looking at the data and knowing our data. I think it's more important to like know what we measured and use a lot of plots or whatever. But generalized mixed effects models are actually very popular now in my field in psycholinguistics, and it's very hard to publish a paper when you don't do them because reviewers look for them. So we use them a lot. Sometimes they don't add a lot of values based on the regular GLM. Sometimes they do add a lot of value because they compensate for this clustered data, right? Yeah, I will say feel free to reach out to me via email or WhatsApp if you need help with your own GLMs. I already helped Shir a bit, yeah. And I will also send you these links for more tutorials and blog posts and frequently asked questions. All right.
Thank you very much. Can you send us the presentation? Can you send us the presentation?
Yes, of course.